Hello guys, good afternoon. I hope you are having a good time at KubeCon India. So we are here to present a talk that is keeping the lights on, zero downtime application upgrades in Kubernetes. Myself Shashank Pai and my co-speaker is Sagar Jadhav. So we are here to present before you some scenarios which can help you achieve zero downtime and keep your Kubernetes applications resilient. So we'll take you through a scenario where a company has just moved to a Kubernetes cluster. They are into production and they are having a tough time handling them. So they are stacked up with lot of client tickets, on-call requests, and revenue is going down. So seems like a relatable image, right? And if you are using Kubernetes, more relatable. So I'll ask my co-speaker to take you through few strategies. That is first strategy, that is health check. Sagar, on to you.
Hey, hi friends. So in the last slide, we have seen that the war room is going on and the manager is asking like, my application is down, and engineers are giving some sort of solutions like that we could do this, we could do this. And then the engineers decided let's go and identify what could be the possible issues with the application. So they have started looking into the logs, and one engineer found that the application pods are keep on restarting continuously. So then they just describe the pod definition and identify that the liveness probe and readiness probe are pointing to the same endpoint, which could be the possible solution why my application pod is restarting. So we'll take this problem statement, and in next couple of slides, we'll understand what is this issue and how can we recover it from it. So before understanding the issue, let's set some context around the health checks and the props. So you might be aware that whenever there is a situation that node is running out of resources or the application is running out of resources, Kubernetes try to reschedule that pod into the healthy node, right? So that issue is sorted out. But there could be a scenario when your application itself is stuck. It's not accepting new requests. It's not able to process the request. So from the client side or from the observability point of view, your application pod is running, but it's not serving any requests. So how can Kubernetes identify such scenarios? So it definitely needs a signaling or a mechanism through which it identifies that this particular application is not working as expected. And as we know that each application has its own working, so we cannot have a generic solution for it. So that's where the Kubernetes introduces two probes, basically liveness and the readiness probes. And each probe has its own significance. So what Kubernetes does is it tries to probe a container and identify what is happening with the application. So with liveness probe, it tries to check whether the application is running. And let's say if identifies that application is not running, it tries to restart the app just to make sure that the application will be working in the next subsequent run. And in the readiness probe, it identifies whether my application is ready to accept the traffic. For example, I have a front-end app which is dependent on the backend, but if the backend is not working, front-end will not work, right? So in that case, if the readiness probe fails, it will move that pod from the pool of the pods where the traffic is serving. So for both of this probe, although in both the cases we are probing the container, but the way Kubernetes handles this probe is different, right? So there are some best practices that we should check on while designing this probe. And these are the three important aspects. We have worked on certain scenarios, and that's where we identified that if you're designing the liveness and readiness probe, you should make sure that both the probes should have a dedicated endpoint. And in our previous slide, we have seen that the engineer identified that both the probes are using the same endpoint, right? And we also know that if the liveness probe failed, Kubernetes restart the application, right? But let's say my application is running, but my dependent application is not running. So why should I restart my app, right? So that's where we should have a separate endpoint for both of these use cases. Second thing is this important one. There are scenarios that I've spoken about, like we have in the microservices architecture in the distributed world, one service is dependent on another, like backend is dependent on database. So we want to make sure that backend should handle the request only when database is available. So for that, what we can do is we can design the readiness probe in such a way that it can do a SQL query to the database just to check whether the connection is happening or not, and then it should mark that pod is now ready to handle the request, right? So this is the second important point. Third one is like these probes are nothing but the endpoints, right? So just to make sure that your probe, because these probes are continuously, Kubernetes is trying to, after a certain period of time, it is continuously trying to check whether your application is running or not. So just make sure that your probes endpoint should give a simple response, like status code. We don't want the JSON response to be there. So we have solved one issue, okay? Now, engineer and these two engineers are again try to identify what could be other scenarios. So when the application update is happening, right? One engineer found out that the old version pods are not available and the new version pods are taking some time to up, right? So so there are some like 10 or 20 seconds of delay for which the application is not responding, or there is a downtime for the application. Why? Because somebody has mistakenly set the max unavailable to 100%, okay? And the max surge is set to 0. We'll see this configuration in the later slides, but this is what the issue that we have found out, right? Now, before going deep into those configuration, let us first understand what are the different different update strategies that we can follow. That is there in the Kubernetes. So Kubernetes like natively supports two, like rolling update and the replacement. But we'll talk only about the rolling update because it allows us to do the zero downtime upgrade. And there is one more strategy that we will talk about. It is not supported natively by Kubernetes, but through the other toolings, we can have that in place, right? So what happens with the rolling update? In case of rolling update, the new version pods are gradually roll out until and the older version pods are terminated once the new version pods are available. If you can see this diagram, we have one new version pods are running, then only the one older version pods are terminated. So this is like gradually rolling out. So the advantage of this is your application is available throughout the upgrade process, right? But there is one issue with this approach, that there are scenarios that for a certain period of time, your two versions of your application is up at the same time. So you have to make sure that your database schema and the backend should be able to handle such kind of request. Okay, so this is one constraint with this approach, and we'll see in the next strategy how can we solve this particular constraint. And and one more important advantage is if you have configured the max search properly, right? So then there is a minimum additional resource usage during the deployments. For example, you have set the max search to 1, okay? Then only one pod is created first. One is, in that case, only one extra pod. So one extra pod is consuming the resources. But let's say if you have set it to 100%, that means if you have 5 replicas, so then the 10 replicas, 10 pods are running at the same time. That will consume a lot of resources, right? So for the production, like we have gone through a couple of scenarios, and what we recommend to our own customers is for the production scenarios, make sure that you have max unavailable to 0. That means your application is up for all the time, and max search is set to 1. Although this will reduce the update process because only one pod is progressing at a one time, but it makes sure that your application is live for all the upgrade process. So this is just a code snippet of how you can configure the rolling update strategy. Next. So we talked about the constant, like in the rolling update, we have to make sure that the backend and the database should be sufficient to handle such kind of request, right? Now the manager is talking to an engineer, and she was saying that can there be another approach? Okay. One other thing is that both the applications are moving at the same time, right? And they wanted to make sure that my new version application should be tested first, then I should be able to switch my traffic from the old to the new one. So the engineer suggested that we can have a blue-green deployments in Kubernetes. Okay, so let's see in the next slides, how can we achieve the blue-green deployment in Kubernetes? So in Kubernetes, although there is no native support in place, but what you can do is we can have a new version deployment deployed alongside with the old version deployment. Okay, and then you can have your test team tested the new version deployment completely, and then using the different network switches, you can switch the traffic from the old version to the new version. So here we are resolving that constant, right? In this case, we don't have to make sure that the backend needs to support both old schema and the new schema, because here at a time only single schema or single version is available. The only problem with this approach is it will consume the cost, because at the same time you have two versions of the application running. So if you have a customer who is running out of who has some budget constraints, right? So don't recommend this approach, because in this case you have both the versions up at the same time. Okay? Yeah. Let's go to next. Now we have identified two issues, right? With respect to props and with respect to update strategy. Now here, the architect comes in. In the previous slide, the manager is asking about the different strategy. Now here, the architect comes in, he is talking to an engineer that I was looking at the Kubernetes, I was looking at my Kubernetes environment, and I saw that few of my application pods are terminating with the 500 status code. So he was trying to delete that pod, but it was failing, and in the logs, it is getting the 500 status code. So then this particular engineers figure out that he looked into the code to make sure that what's the actual issue. So when he looked at the code, application code, he found that we have not handled the SIGTERM signal properly. So there is no cleanup happening. Basically, this particular application is handling some file system thing, and when we are deleting the pod, the file system connection are not close, so it is giving some errors. So he recommended that we should handle the SIGTERM signal properly to make sure that whenever this application pod is deleted, all the cleanup should happen, okay, and all the in-fly requests should be completed on the time. So this is also one of the recommended strategies which we should follow to achieve the zero downtime upgrades. So let's discuss more about this. So this SIGTERM signal is the Unix construct, right? So in the Kubernetes world, what happens is whenever you delete a pod, right, Kubernetes sends the SIGTERM signal to the container with the PID 1. Okay, and it waited for a certain period of time, and then if for the given time, if the application is not gracefully shut down, it sends a sick kill signal, because of which the application shut down abruptly. Now here two things are happening. Either you can shut down the application gracefully, or you can shut down the application abruptly. So what is the recommended strategy, right? We should shut down the application gracefully, right? So that we can do the cleanup or we can handle the in-flight request properly. So for that, there are two concepts that we can use here. First thing is the lifecycle hook, which Kubernetes supports out of the box. Second thing is you can add the graceful handling in your code itself. Whether you are writing your application in Golang, Python, there are packages available through which you can listen to that SIGTERM signal and do the cleanup method. So let's understand the whole flow through a diagram, right? So I executed kubectl delete pod command, okay? Then what happens? Kubernetes trigger the pre-stop hook, okay? It waited for it to complete it, and then it sends a SIGTERM signal to the application. And then it waited for it to be so that it can be gracefully shut down, right? Let's say if within 30 seconds, if the application is not shut down by itself, it sends a sick kill signal to delete that to exit that particular application, right? So this parameter is very important. So make sure that this parameter has a sufficient value so that your pre-stop hook and graceful shutdown should be completed in a given period of time. We'll talk about some of the best practices, and these are the important ones. Best practices regarding the pre-stop hook, right? First point I already discussed, right? We should have a proper value of the terminate grace period second, because it could be the case that in your pre-stop hook, you're calling the load balancer to deregister your service, but that whole like connection request and response took so much time, and you have set only the 30 seconds period, right? So make sure you have a proper value set. So you can do some hit and try with your test environment and come up with the value for the termination grace period seconds. Second thing is, one more use case with the pre-stop hook that I forgot to mention here is, let's say when you delete your application, right? What Kubernetes does is, it deregisters your pod from the from the pool of pods who are receiving the traffic, right? And in case of the production or the cloud environment, it typically be a load balancer. Now, what happens is the deregistration took some time, and it took some time, but still some requests are went into your pod for the handling, but the application is exiting out, right? So those in-flight requests are not properly handled. So from the end user, they are like accessing the application, but they are not getting the proper responses. In this case, what should happen is as soon as you have deleted the pod, right, your application should be unavailable or some other pod should be handle that request. So what we can do is in the pre-stop hook, you can have that code in place which does the deregistration by itself, wait for the success code, and then allow Kubernetes to send the signal to the application. Third point is you should have your pre-stop hook script should be fault tolerant. What does it mean? Even if your pre-stop hook fails, then also Kubernetes sends a SIGTERM signal to your application. So in that case, there will be that handling will be incomplete. So make sure that you have added all the retry logic to make sure your pre-stop hook works successfully. And last point is from the what all the things we have talked about is about the deployment configuration and from the admin point of view. But last point is for the developers. So in the next slide, we'll just look at the example of how you can configure how you can handle the SIGTERM signal in the Go, right? So this is an example wherein you have the channel set up and then you're listening to that channel. Once you have received a SIGTERM signal, you can do some cleanup logic and then you can exit from the program. So this is the recommended approach to handle the SIGTERM signals. Now over to Shashank for the next couple of slides.
Thank you, Sagar. So now we had a look at how health checks as well as pre-stop hooks handling application gracefully has rectified at a certain level for the company. But now what they are facing is one of the app in a zone has completely gone down. What was the cause? Because all the pods are deployed in the same zone. What can be the solution for this is being asked to the engineer. The engineer comes up with a solution that is topology spread constraints. So let's see what topology spread constant do. So the application pods, for example, on your left side, the application pods are scattered, whereas we have zone A, zone B, zone C, given by a cloud provider. So what topology spread does is, it helps you spread your pods across all the zones available. So in this way, even if my zone C goes down, I have my pod available in zone B, zone A. This will help me keep my applications up. So what are the pros of topology spreads? That is preventing resource bottlenecks. We won't be relying on one zone. Second is balancing load and improving fault tolerant. So here is the example on your right, which gives you an understanding of what topology spread constant is. So few of the best practices that we'll recommend setting topology spread is, make sure you set the max queue carefully. So what max queue does is, it will help you provide a balance. So the number of imbalance you can have, maximum number of imbalance you can have. So maximum we'll prefer is 1. It should be at a minimum level. You can't afford to have a more imbalance across your cluster. Second is plan to recover from zone failure. Even if you have topology spread constraints, make sure you are able to get over your zone failures. That can be done by monitoring or checking your zones throughout. And one of the last thing is, make sure you use the do not schedule thing very well. Because what do not schedule does is, when you say do not schedule, it will make sure it will not be scheduled in the zone which has gone down until the zone comes up. So for example, if your application needs a quorum or a balance of 3 pods and you have set do not schedule, it will not schedule in the 3rd zone. So because of this, you are left with only 2 pods in 2 zones, for example. You can use when satisfiable as schedule anyway. So what this will do is, it will schedule your pod in the other nodes that are up. And when the 3rd node comes up, it will schedule there. Yeah. So we have fixed the topology spread constraint. Now what these guys are facing is their pods are getting evicted and they have come back to the engineer. What can be the reason? Why my pods are getting evicted due to node pressure? So what can be the fix of this? So turns out the engineer finds out the deployments or the workloads that are being deployed do not have CPU and request configured at all. So what CPU and request have to play and what scheduler does? So scheduler is responsible for scheduling your pods on nodes. Depending whichever node is healthy, it will schedule on that. But what does request and limits have to play here? So when you give a request to a deployment or a pod, it makes sure to find a best node for you. For example, if you give a request of 1 GB RAM, it will make sure to allot it on a node where it has at least 1 GB available. For example, a node has 5 GB, it will allot that pod to that node. So this way, scheduler looks for request. And if there are no requests, the pods which don't have any request or limits will be first one to get evicted. But why is the case? We'll look forward. So as you can see on your left side, there are pods which are having request and limit set. And they are allotted a proper node with proper memory or CPU. So for example, all these pods on your left are allotted a node checking the memory. The scheduler will make sure it allots to that node. But whereas on the right, there are few pods which don't have any CPU request allotted at all. So they are having allotted to the node. So that node has some sparse capacity available, it will be allotted over there. So, but they will be the first one to be evicted. So let's see what request and limit actually are, how they help. So request is the minimum requirement your application needs. For example, my application needs a RAM of 1 GB. It will be the minimum requirement and I'll set the request as 1 GB of RAM. Whereas the limits will be, for example, I think my application will burst up to 2 GB and that's the limit. It cannot go above that. So memory and CPU. So memory can be configured in form of kilobytes, megabytes, gigabytes, as well as CPU, whereas CPU are configured in form of cores. 1 core of CPU I can allot, 2 core of CPU depending on my request and limits. So yes, so next is what limits does to you, what limits impact on CPU and memory? What are the impact of that? So when you say I have given a limit of 1 GB RAM, when it reaches that limit, it will be restarted, OOM killed. It goes out of memory. Whereas it is not the same case for CPU. The CPU, when it goes to the limit, it cannot go above that and it will be throttled, and which will bring a slowdown to your application. So yes, so next is on what basis the application is prioritized. For example, I have a workload which is of high priority. Consider the application which the company is facing a downtime on. So that's a critical application, right? It is bringing a revenue to your company. So those are supposed to be mission critical application and those need to be prioritized. So those priority are in form of QoS classes, quality of service. So there are 3 classes: guaranteed, burstable, and best effort. So when I say guaranteed, you are giving a request and limit as same, that is 1 GB RAM and 1 GB limit. 1 GB RAM as request and 1 GB RAM as limit. And same for CPU. So those are guaranteed. And for burstable, it will be a different. For example, I think there is a request that I need to be allotted as 1 GB, but my application might burst up to 2 GB. The limit I can keep as burstable. And best effort are the ones which are not given any request and limits at all. So guaranteed ones will be given the highest priority. And in that order only, applications will be evicted. So the best effort pods which don't have any request and limits will be the first one to get evicted. Next is burstable, and after is guaranteed. So yes. So next, one of the same things to give a priority to your application is a priority class. So consider priority class as a ticket that you have reserved for your bus. That's the reserve that you can, no one can take it. Same is for priority classes. You can allot a priority class to a workload. For example, I have a production workload and I can allot a highest priority to that workload. Second priority, I can give it to a pre-prod environment. And the last will be development one. So in this way, I keep a check that my highest priority pods are always protected. So yes, so some best practices that we like to share while setting requests and limits are, it will be for your mission critical pods, always make sure you set a request and limit. Second is pair it up with pod disruption budget. We'll look at pod disruption budget in next section. Then you'll get to know what I'm talking about. But make sure to pair it up with pod disruption budgets. The second, one more debate that I would like to bring over here is there is a widespread debate in the community that you should always set request for CPU. Why is that case? Because we just observed, right? For CPU, when it reaches the limit, it throttles. It makes your application slow. So when you set a limit and when you don't know what the limit is going to be, so better not to set request. But then you have a case wherein if you set a request and not limit, you take the advantages of QoS classes. So that class becomes burstable instead of guaranteed. So the what our recommendation is, keep a good check, monitor your application, how it is performing, benchmark it, let it go through a heavy testing, and then you will get to know what your application needs are for CPU and memory. This way you can set your request and limits. Yeah. So the last part is always make sure for memory, try to keep the request and limits same. That is 1 GB RAM, 1 GB request and 1 GB of limit. Don't make it very low. Yeah. Now there is another scenario that has come up. That is, now we have rectified a lot of issues, but now the company is going through some pod disruptions in case of node maintenance or cluster upgrades. So these come into the class of voluntary disruptions. So how to get rid of that? So whenever there is a node maintenance happening, the pod is going down and disruptions are happening. So how to get rid of that? So the solution to this is, the engineer has to say is, let's use pod disruption budget. So what pod disruption budget is, it enables you to control the number of pods that can be unavailable during a voluntary disruption. So for example, I am having a node maintenance, and during that time, all my pods are going down. Giving a pod disruption budget, what it will do is, it will make sure at least one or whatever thing you have set, it will make sure that is available. So you don't face downtime during those voluntary disruptions. So that those number can be set using max unavailable and min available. Either of them you can use. So max unavailable, what it does is, it gives you a number of pods that should be unavailable at the same time, the maximum number of pods. Min available is saying that these number of pods should be available, that minimum number of pods should be available. Just to make sure, understand that PDBs will not work on involuntary disruptions like node pressure or some disruptions that are not under our control. These are for voluntary disruptions that are node maintenance or cluster upgrades. So next, we'll just have a look at a scenario where there is no pod disruption budget, whereas a scenario where there is a pod disruption budget. So as you can see, when there is no pod disruption budget applied, the node is taken down for maintenance. All the replicas, both the replicas go down at the same time before they are becoming available on the node 2. So in that brief time or whatever time it takes to come up, there is a downtime. So this mainly happens during upgrades. So when you pair up with pod disruption budget, you have one replica going down, the second replica is made available on this second node. This is because of setting of max unavailable or min unavailable. Min available, sorry. So in this way, two pods are available on the second node and your node is taken down for maintenance. So this way, we are always keeping the application up, even during maintenance. So one of the few of the best practices that we'll have to tell are configure PDBs carefully. Make sure your pods are not in crash loop back off. So what crash loop back off does is it will term the pod as unavailable. Due to this, if all pods are unavailable and you have set a unavailability of 1 and there are 3 pods becoming unavailable, the involuntary disruption, voluntary disruption that you have cannot go forward, right? Because max unavailable is more than what is set. There are more pods that are unavailable. You won't be allowed to do the node maintenance or cluster upgrades at all. Second is use accurate selectors. If you mess up with the selectors through a typo or something, it is not going to consider it at all. You will believe that you are protected through pod disruption budget, but actually you are not. The pod disruption budget doesn't be there at all. Third is set max unavailable or min available carefully. That is either use max unavailable or min available, because you can use either of them. Don't mix and match to create more confusion. Also, other thing is use max unavailable with percentage. You never know how much pods scale for your application. If you keep one, that will only have one available, whereas your application might need more. So always keep it in percentage. Last is do not use a value of 0% or 100% for your service. So always use more than that. Not okay. So I think we have come to a stage where we have made the application resilient. We brought the company to a stage where we can say that using these strategies at least, we can keep their application running well. So few of the takeaways that we just went through are request and limits. It is always advisable to use request and limits. Never keep your application without these configs. There are more chances of your applications going down or your pods getting evicted. Second is always design good health checks. As we saw in health checks, if you have a endpoint with the same, if you have both liveness and readiness with the same endpoint, you might end up having cascading failures and you might have more issues. Always make sure that you design your health checks well. Third is graceful shutdown, which we saw through pre-stop hooks and application gracefully shutting down. Make sure you handle that in your code itself. Last one we saw through QoS classes and priority classes. So always make sure you use either of them. Make sure you use priority classes. Highest priority should be given to your applications which are more critical, and lower one to the ones which are not so critical. We also looked at cluster level strategies. The last one being TopologySpreadConstraints, where you can distribute pods among all the zones. And last one being pod disruption budget. Always make sure you limit your disruptions. So when you are having a voluntary disruption, always the pods are available when you are having that. So you don't face any application downtime. Yeah, so these are the takeaways. So now I think the company is more aware that just using Kubernetes will not give you out of the box resiliency. You have to use some strategies and you should implement them well. So that were our key takeaways. So here is a QR code where we are publishing a book a short book wherein these strategies are explained in more detail with maybe a few examples, which will be available. Just add it and you will be added to the wait list, and whenever it is available, it will be delivered to your inbox. Yeah, thank you. And before we go, we have these are our QR codes. We are there on LinkedIn. We are happy to connect.